As we start our new unit on magnetism, we need to define a pretty important term. It's called the magnetic domain. A magnetic domain is a tiny little region inside what we call a ferromagnetic material that we represent by an arrow. Now, before we really talk about this magnetic domain and really understand what it means, we have to define a ferromagnetic material first. Does everybody know what a ferromagnetic material might be? Think of the word. Okay, think of the word ferromagnetic and maybe where that word ferromagnetic might come from.
Metals that can be magnetic.
Yeah, it's something that can become magnetized. Now, there's not actually a big list of ferromagnetic materials. It's fairly limited, actually. The most common ferromagnetic material, again, if you look at the word ferromagnetic, you might predict what the most common one is. Iron. Yeah, chemical symbol for iron on your periodic table is Fe. Cobalt is also a ferromagnetic material. Nickel is also a ferromagnetic material. There's a few others as well, but it's not a huge list of materials that can become magnetized by ferromagnetism. Alloys of these do as well, right? Steel. Okay, you stick a fridge magnet to your refrigerator. Of course, the refrigerator attracts the fridge magnet because the refrigerator is ferromagnetic. It's not made out of iron per se, it's made out of steel, but steel is an alloy that consists of iron. So other materials that are alloys of this iron, cobalt, and nickel, and so on, will be ferromagnetic as well, have the potential to become magnetized as well. All right, now we have a little bit more perspective so that we can actually understand what this magnetic domain is. This tiny little region inside this material that's represented by an arrow. If we were to take a look at a ferromagnetic material under this high-powered, crazy microscope, it's not like we're going to see a bunch of little arrows. We might see regions, okay, regions of alignment, but we're not going to see arrows per se. We simply represent alignment of these by arrows. So when we align these domains, when these domains aren't aligned, these tiny little regions with arrows, or represented by arrows, are pointing in seemingly random directions. Then we have a non-magnetized ferromagnetic material, just a piece of steel or a piece of iron right now. If we want to make it magnetized, then we've got to actually align these domains or cause these domains to point more or less in the same direction. Now, when we do that, and I'll tell you in a few minutes how you can go about doing that, but when we do that, these domains no longer look like they do in the top diagram. They start looking more like this, pointing in the same direction, or at least pretty close to the same direction. We arbitrarily define, and it is arbitrary, we could define it the other way around if we wanted to, but we have to be consistent. As long as we're all talking the same language, it doesn't really matter which way we define the direction of the domains, but we do have to be talking the same language. In order to talk the same language, we arbitrarily define the domains as pointing towards the north end of a magnet. So in other words, this second second ferromagnetic material that I have drawn here, which is magnetized, has a north pole and a south pole. The south pole on the left where the field, where the magnetic domains are coming from, and a north pole on the right where they're pointing to. What do you think would happen if I took a hacksaw and cut this magnet in half? What happens? You get two magnets, right? One magnet is a north, and one magnet is a south, right? You would end up with something like this. Correct? No, if you cut it in half, you're still going to have domains. And the domains are still going to point towards the right. Like this. Which means, because of the way that we define the direction of the domains, that this has to be a south and this has to be a north. The magnetic domains point from south to north. And similarly on this one, we have to have a south pole and a north pole as well. There's a lot of similarities between electricity and magnetism. One of the fundamental differences is that in electricity, we can have a single charge. It's easy to have a positive charge by itself or a negative charge by itself. We can't have a single pole. You cannot have a magnetic monopole, just a north pole or just a south pole. As crazy as the shape of a magnet might be, as odd as it might look, as difficult as it might be to find in a particular magnet, the north pole or the south pole, every magnet has a north pole and a south pole. So, we got a magnet. Domains are aligned. How do we make that happen? How do we get those domains to become aligned? Well, there's two ways. One, this is the easiest way, and you guys have probably done this in elementary school. In fact, you've probably done both of them in elementary school in some magnetism unit or something. Bring another magnet nearby. When you bring another magnet nearby, the aligned domains in that first magnet, and the thing that's already magnetized, will cause either a temporary or a permanent alignment of domains in the second non-magnetized ferromagnetic material. So it might look like this. Here's object number one with domains pointing in whatever direction, like this. Here's magnet number two. This is actually a magnet because we have the domains already aligned, pointing in one particular direction. This has a polarity associated with it. This would be the south pole, this would be the north pole, because we define the direction of the domains as pointing toward the north. The domains in this magnet that's already there will cause the domains in this non-magnetized ferromagnetic material over here on the left to start aligning. So now instead of pointing in pretty much random directions, they start pointing in the same direction as the original magnet. Now we got a magnet over here. On the left-hand side, we got a polarity, south pole over here, and a north pole over here. What do you think happens to these two things? They're going to attract each other, right? Yeah, they're going to attract each other. We've just caused the domains in the non-magnetized ferromagnetic material to become aligned, probably temporarily, but the polarity of that thing that was non-magnetized is now such that the north pole of that will attract to the south pole of the permanent magnet. In other words, this magnet is going to attract this previously non-magnetized ferromagnetic material. That's why when you take the fridge magnet and you put it against the fridge, it sticks to it, right? It temporarily aligns domains in the steel refrigerator door, which turns that one section of the steel refrigerator door into a magnet with a polarity that causes an attractive force with that permanent magnet, that fridge magnet that you stick against it. So bring another magnet nearby, cause an alignment of the domains. Now the second way to do it is to use an electric current. We'll talk more about this tomorrow. But I'll just briefly tell you that I do not mean run an electric current through the ferromagnetic material. If you've got a piece of steel, the leg of your desk is a piece of steel. It consists of iron and some other materials as an alloy. If you run an electric current through the leg of that desk, you're going to electrify it. You might shock yourself, but you're not going to cause it to become magnetized. If you took a wire and wrapped a wire around that steel leg and applied an electric current through the wire, then you would magnetize the steel leg of your desk. So you use an electric current, but it's not an electric current going through the ferromagnetic material. It's an electric current going through a wire that will generate a magnetic field that will cause the steel leg to become magnetized. Again, we'll talk more about that in a little bit more detail tomorrow. So, bring another magnet nearby. The magnetic field from the first magnet causes the second magnetic field to form or to align, or you can wrap a wire around, apply an electric current. That will generate a magnetic field, which will magnetize the non-magnetized ferromagnetic material. Both of these involve using an external magnetic field. The first external magnetic field comes from a magnet. The second external magnetic field comes from an electric current. Question? Yes, like producing electricity with magnetic fields? Oh, you mean like the induction coils, like for like one of those stoves, like not the typical stove top that you'd have in your kitchen, but one of those portable ones where you use the special pots. Yeah, to be honest, I'm not sure exactly how that works. Yeah, we should look that up actually, because I'm virtually positive it would involve magnetism. I'm just not sure exactly how it is. What he's talking about is those stove tops. They're not hot, right? You turn them on, it's not hot. You can touch it. It doesn't burn you. But yet you put a pot on it and it heats it up. It somehow heats it up without being hot. Again, I'm not sure exactly how that works. We don't typically address that here. It's a good question though. I don't know exactly how it works, but we should look that up and see if we can figure out how it works, see if it does have some relevance to what we're talking about for sure. All right, let's talk about 3 laws of magnetism now. 3 laws of magnetism that are pretty similar to the 3 laws of electricity that we learned in our last unit. First law of electricity was like charges repel each other. So positive repels positive, negative repels negative. Well, similarly, we have like poles repelling each other. North repels north, and south repels south. Remember, we're not talking about positive and negative anymore. So don't say, if I ask you this question, don't say like charges repel. They do, but that's not a law of magnetism. Like poles repel. North repels north, south repels south. You can imagine what that second one's going to be now. Connor, what do you think that second one's going to be? If like poles repel each other, then opposite poles or unlike poles are going to attract each other. Right, north attracts south, and south attracts north. Positive attracts negative as well, but that's a law of electricity, not a law of magnetism. Poles and charge are 2 completely different things. There is a relationship between electricity and magnetism, but they're not the same thing. You guys remember the 3rd law of electricity? This was the hardest one, the one that we said near the beginning of the unit, and then we explained why it happens later on in the unit when we talked about charging objects by conduction and induction. Remember the 3rd law? Charged? Yeah? Yeah, good. A charged object will attract a neutral object. And that's going to happen because of induction, right? Of induction, specifically a temporary separation of charge. When you bring a charged object nearby a neutral object, the near side of the neutral object becomes opposite and therefore attracts. What do you think the 3rd law of magnetism would be? Hint, it's not charged objects attract neutral objects. We don't talk about charge and neutral with magnetism. Rather, yeah, magnets attract non-magnets. Well, not all non-magnets. If you take a magnet nearby a piece of paper, what happens? Nothing. You bring a magnet nearby a piece of plastic, what happens? Nothing. A piece of glass, what happens? Nothing. Piece of wood, what happens? Nothing. You bring a magnet nearby a piece of iron, what happens? It's attracted, right? So we have a magnet, or north or a south pole of that magnet, attracting not just a non-magnet, but specifically a ferromagnetic non-magnet, or a non-magnetized ferromagnetic material. As I write this, I probably should have said this a little bit shorter. Both north and south poles of a magnet, or we could just say a magnet, right? Either end of a magnet attracts a non-magnetized ferromagnetic material. Why does it have to be a ferromagnetic material? Why can't a magnet attract a piece of paper? Because in a piece of paper, you can't temporarily align the domains. You don't have the domains. You can't temporarily align something that's not there. If you bring it nearby a ferromagnetic material, you can temporarily align the domains in this ferromagnetic material. When you bring the fridge magnet nearby the fridge, you temporarily align the domains in the fridge, steel door of the fridge. It causes the steel door to become a temporary magnet and therefore attract. Remember the diagram we drew a few minutes ago? This was our non-magnetized ferromagnetic material where domains are pointing in random directions. This is our magnet with our south pole and our north pole. That causes these domains over here to temporarily align, causing a polarity that looks like this. So this original non-magnetized ferromagnetic material has a temporary alignment of domains, which causes now a force of attraction between the north and the south. So it's not completely unlike charged objects attracting neutral objects because of a temporary separation of charge, induction. This is a magnet attracting a non-magnetized ferromagnetic material because of the induction of a temporary alignment of domains. Now, what about the magnetic fields? We alluded to this earlier on. We talked a little bit about magnetic fields a few minutes ago when we were talking about how we generate a magnet, how we produce a magnet. We said we bring another magnet nearby, or we wrap a wire around a piece of steel or something like that and apply an electric current through it. An external magnetic field, however it's caused by another magnet or whether it's by an electric current, an external magnetic field will cause magnetism. But what is a magnetic field? You guys remember how we defined an electric field? I think you do, because last Wednesday when you had your unit test, question number 1 on your unit test was define an electric field. And you guys nailed that question. An electric field, go ahead. Yes, it's a region in which an electric force could be experienced if there's a charge there to experience it. So what do you think a magnetic field is? Electric field, a region in which an electric force could be experienced by an electric charge. Magnetic field would be, Dylan, you look like you want to tell me there. Yeah, it's a region in which a magnetic force could be experienced by something. Specifically, that something would be a magnet or a ferromagnetic material. A region in which a magnetic force could be experienced by another magnet or by a ferromagnetic material. Magnetic fields are caused by magnets, and they're also caused by electric currents or moving electric charges. We'll talk about the moving electric charges thing here, as I say, a little bit more tomorrow. Why that happens, how it happens, what the magnetic field looks like, and so on. So you know now, it can be caused by an electric current or moving electric charges. Magnetic field, a vector field or a scalar field? What do you think? It influences things. Does it influence things in a particular direction or just influence things in no particular direction? It would be a vector field, yeah. You're right, it would be a vector field. As opposed to, say, this space heater up here that's influencing me, this heat field is influencing me, but not in a particular direction. That would be a scalar field. Yeah, an electric field, a gravitational field, a magnetic field, they're all vector fields. By the way, the symbol for magnetic field is B, with the little half arrow over it, indicating that it's a vector field. The unit for magnetic field is a capital T, which stands for Tesla. The strength of magnetic fields vary vastly. The strength, let's say, of the Earth's magnetic field. Even the Earth's magnetic field varies dramatically, depending upon location. But on average, it's about 10 to the minus 5 Tesla. 10 to the minus 5 Tesla. Although it's changing. In the last 50 years or so, it's decreased like 10% or so. In fact, it's decreasing so quickly. The strength of it is decreasing so quickly that there's some thought, and it's gaining traction in scientific circles. For the last 15 years, 20 years or so, there's been some thought that this is happening, but I'd say the last few years, I've read more and more about it. There's some thought that the Earth's magnetic field might actually be in the process of reversing. It happens on average about every 250,000 years. We know that from geological records, including hardened lava, the magnetic fields that's kind of frozen in hardened lava. Happens on average about every 250,000 years. But it's actually been about 750,000 years since this happened the last time. So we're about 500,000 years overdue for it. And the Earth's magnetic field is decreasing quite dramatically as we talk, which leads some scientists to believe, at least that's part of what leads some scientists to believe, that we might be in that process of reversal right now. Another 100 years, 200 years, the North Pole might actually be the South Pole, and the South Pole might actually be the North Pole. We don't know. Okay, we don't know. Right? What would cause that, you mean? That's the funny thing, actually. That's a great question. But the answer to the simple answer to that question is we have no idea. We don't know what causes it. Scientists don't know what causes the magnetic field reversal. We know that it happens because of evidence, lots of forms of evidence, including, as I say, magnetic field that's kind of frozen in time with different volcanic eruptions in the hardened lava. We know that it reverses, and we know that it's usually pretty timely, just not this last time. But we don't know what caused it. We don't actually know completely what causes the Earth's magnetic field to begin with. So it's hard for us to understand what causes a reversal when we don't even really know what causes the magnetic field to begin with. We think it has something to do with the churning magma within the Earth and charged particles in that churning magma moving around, but not sure exactly. And it's not just me or us that are unsure. It's generally humankind that's unsure of what would cause it. The effects of it, on the other hand, we understand some of the effects of it. Okay? One of the things that the Earth's magnetic field does is protects us from charged particles from space. Okay, charged particles get deflected by the Earth's magnetic field. Well, if the Earth's magnetic field decreases to the point where it's zero and then increases as it reverses, then there's going to be a period of time where we're not protected from those charged particles coming from the sun. Not magnetically, at least. The Earth's atmosphere offers some protection, so it's not like all of these charged particles are all of a sudden going to bombard us. But we're less protected, certainly dramatically less protected than we are right now. Navigation becomes an issue, right? Although not so much now with GPS, right? But you had a question? Okay. Yeah. There would be, yeah, there would be, the energy grids could be taken out, satellites could be taken out, not so much by the reversal itself, but by those charged particles that are coming from the sun that are bombarding them could wreak havoc with that, yeah. Yeah.
And are there certain animals that use like the magnetic field kind of for navigation purposes?
Yep.
Geese and stuff.
Yep.
So if it's fully going to reverse and be zero.
Are they going to start flying north? Is that what your question is?
How would
Flying
it
north
affect the
and
animals? Because they've obviously adapted to
Yeah.
all the directions.
Yeah, that's a good question. But the other thing with that is, like geologically, this actually happens quite often, right? Like every 250,000 years or so. Well, animals have still managed to adapt over that relatively short period of time, even those animals that do depend on the Earth's magnetic field. So I'm not sure. I'm not sure, like if they could adapt. Like the mechanism by which they use, the biological mechanism by which they use, I would assume would take probably millions of years to adapt. But the decision or the instinct perhaps could adapt over a fairly short period of time. It's like if I have a compass and all of a sudden my compass is pointing in the wrong direction, well then I just look at the other end of the compass, right? Does that make sense? So I don't know if animals, I don't know the answer to that question, but I don't know if animals might do something similar to that. Kind of just look at the other end of the compass, so to speak. But perhaps.
Go the wrong direction, lives.
Sorry?
Whoever doesn't go the wrong direction lives. So.
Yeah. Basically, that's it. Like the mechanism inside doesn't change, but those that go in the wrong direction don't come back in the spring. So then the next year they say, well, we're not going that way. We better go the other way. It might take a couple years to figure that out. But so the Earth's magnetic field is pretty weak. It's weakening, but it's already pretty weak. A bar magnet, about 10 to the minus 2 Tesla. So on average, a bar magnet is about 1,000 times the strength of the Earth's magnetic field. We think of the Earth's magnetic field as being pretty strong, affects compasses, right? But a bar magnet, you're going to use a bar magnet in a few minutes on a little activity you're going to do. They're about 1,000 times the strength of the Earth's magnetic field. Anybody ever had an MRI? Nobody? You guys are healthy then. This morning there was like 5 or 6 people that had an MRI for one thing or another. You go get an MRI, they ask you all these questions. Like it's this massive questionnaire to get an MRI, including whether these questions you think are silly questions, like, have you ever had metal in your eye? Oh, so what? So what if I ever had metal in my eye? So what? No, I haven't actually. Yeah. Yeah, see, that's the thing, right? The Earth's magnetic field is 10 to the minus 5. A typical bar magnet is 10 to the minus 3. A MRI machine is about 15 Tesla, or about 10 to the 1 Tesla. That means 10 to the 1, the MRI machine is about 10,000 times the strength of a typical bar magnet. 10,000 times the strength of a typical bar magnet. That's like Ariel taking 10,000 bar magnets, putting them together in one spot, and then throwing the chair against that, right? It's going to attract it pretty good, right? Which is, in turn, still 1,000 times stronger than the Earth's magnetic field. So it's an MRI machine is actually, say, about 15 Tesla. Up until a couple of years ago, the strongest magnetic field ever made by human beings was about 40 Tesla. So about twice the strength of an MRI machine. There was a lab in, I want to say it was in Japan. I think it was just last year, like last semester, where they produced this magnetic field that was quite a bit larger than that. And it was so big that they actually blew up their lab. Like it actually, I'm not sure what the mechanism for that was, but it actually destroyed their lab. It was such a strong magnetic field. Typically, though, we're talking about 10 to the minus something for magnetic fields. Yep. All right. We're going to do an activity here in just a moment here. Try to find some properties of magnetic fields, directions of magnetic fields, shapes of magnetic fields. Everybody's going to be given a piece of paper in just a moment here. And on that piece of paper is going to have 3 sets of magnets. The first diagram is going to have one magnet with a north pole and a south pole. The second diagram is going to have 2 magnets beside each other with the north pole and a south pole facing each other. In other words, 2 magnets that would attract each other. And then you're going to have a picture of 2 magnets with a north pole against a north pole where they're going to repel each other. Now, surrounding each of those 3 scenarios are a bunch of stars. These are going to represent maps. These stars are going to, on the map, are going to represent locations of where you're going to place a compass, just a regular compass that you would use for navigation in Boy Scouts. I want you to put the magnet on the face of your desk right in the middle, away from the edges, because the edges have the steel bars underneath it, right, which can cause the compass needle to be deflected in kind of an odd direction. So put it in the middle, and then I want you to put a compass needle in various spots as indicated by these stars. And then I want you to draw a short little arrow indicating which way the compass needle is pointing at that star. So at this star, if the compass needle is pointing to the right, let's draw a short little arrow to the right. At this star, if the compass needle is pointing to the left, then draw a short little arrow to the left. Then, once you've drawn all of the arrows corresponding to all the different stars in all 3 diagrams, then we're going to get together, take that data as a class, and we're going to do a little bit of analysis on it to determine the shapes and the directions of the magnetic fields. All right, now that we have all our little arrows drawn in the right directions, we're going to do a little grade 1 activity and connect the dots. You guys should have arrows pointing more or less in the direction that I'm going to draw it here. You might find that they're a little bit different. You probably will find that they're a little bit different because realistically, your compasses have a size to them. Ideally, we would like an infinitesimally small compass to put at a specific spot exactly and see which way the compass needle points at that exact spot. We can't do that. We have to use a compass that's about 4 or 5 centimeters in diameter, which means that we can't get perfect results. But we should see more or less something that looks like this. How many people got something that looks pretty much like this? Good, good. Now, let's do a little connect the dots now. It's going to look pretty much like this. These red lines represent the magnetic field lines surrounding the initial bar magnet with just a north pole and a south pole. The little blue arrows indicate the direction of that magnetic field. You can see that the magnetic field is leaving the north pole and going toward the south pole, kind of like an electric field leaves the positive and goes toward the negative. In fact, if I draw a little diagram below this, you don't need to draw this diagram that I'm going to draw below it here. But if we look at a positive particle and a negative particle and draw the electric field that surrounds that, we would find that that electric field looks remarkably like the electric field that surrounds this bar magnet. You remember that? Now, there is a field line that's conspicuously missing from the second diagram here, and that's this field line that goes in between here, that goes from positive to negative. The reason I chose not to draw that last field line is because the analogy falls apart there. If you look at the field caused by this bar magnet, it looks exactly the same except inside. The magnetic field inside goes from south to north. So it goes the opposite direction. Kind of continues on in a loop here, right? You see that the magnetic field goes from north to south outside, continues in a loop from south to north on the inside. Which makes sense, right? Because the domains go from south to north. That is, the domains simply point in the direction of the magnetic field inside, which is from south to north. Now, what's that second diagram look like? There's a lot more stars on this one. We got a bunch of stars pointing like directions like this. Something like this. How many people got something like this? Yeah? If we start connecting the dots in this one, okay, once again, we see the field lines going away from the north toward the south. Notice the field lines in between join up. What do you think that means? When the field lines join up in between these two magnets, it means that these two magnets will, what is it? Right? Attract each other, right? Just like with electric fields, right? When field lines joined up with the electric fields, there was an electric force of attraction. Here, when the magnetic field lines join up, we get a magnetic force of attraction. One more diagram here. The last diagram, similar number of stars, but this time my stars are going to look something like this. You see they're all pointing from north to south again. Something like this. If we start connecting the dots this time, it's going to look something like this. You can see these field lines are going from north to south, as they always do. That is outside of the magnets. They would go from south to north inside of the magnets. What do you notice about the field lines in between the two magnets? They don't join up, right? And when field lines don't join up, we're going to get not a force of attraction, but rather a force of, this is going to be repulsion. Good. Once again, just like with electric fields. It's a little more important to remember for magnetic fields that we get field lines joining up attraction, field lines don't join up repulsion, because with electric fields, the diagrams tend to be a little bit simpler. We often have like just two charges with the electric fields. Here we've got two magnets, but that's 4 poles. So the field diagrams are a little bit more confusing than they are in the electric field diagrams. Okay, and in the end, remember 2 things. The field lines outside of the magnet goes away from the north toward the south, and field lines join up when they attract, and they don't join up when they repel. We already said that a magnetic field is a vector field. We already talked about that earlier on today. Now we're going to define the direction specifically in 2 ways. One we kind of already talked about. The way that a compass needle points when placed in the magnetic field. That's kind of like the electric field definition. Said the direction that a positive particle moves when placed in the field. So not the direction that a positive particle moves when placed in the field, but rather the direction that a compass needle points when placed in the field. The second one is away from the north toward the south, which is kind of like away from the positive toward the negative. So it's analogous to the electric field again, but not the same thing. The way that a positive particle moves? No, the way that a compass needle moves. Away from the positive toward the negative? No, away from the north and toward the south. I'm going to show you something that's going to rock your world here. This is going to change everything you've ever believed in. Hold on tight, it's right, because if you don't, I can tell you're all sitting at the edge of your desks, you're going to fall off. That's how close to the edge of your desks you're sitting right now. Here's a picture of the Earth. The Earth has a magnetic field in and outside of it. We don't know exactly how the Earth's magnetic field is generated, but we know what it looks like. It looks remarkably like a bar magnet surrounds the Earth. Clearly it doesn't, right? Clearly there's not a bar magnet inside the Earth, but it's like there's a bar magnet inside the Earth. The magnetic field looks something like this. If you erase the Earth there, then it wouldn't look much different than the magnetic field surrounding a simple bar magnet, the magnetic fields that we just drew. Now this is Canada up here. And this is Antarctica down here. This is the equator right here. If I was to take a compass and stand at the equator, which way would that compass point? Towards Canada or towards Antarctica? Which way would the compass needle point? Yep. No, it would. Yeah, it would point one way or the other. That'd point north towards Canada. So if I took my little compass, put it right here, the needle would point this way. That means the magnetic field has to be this way, right? Towards Canada. And it is. The Earth's magnetic field is towards northern Canada. But remember how we defined the direction of the magnetic field. One was the direction that a compass needle points when placed in the field, okay, which we've just established. And 2, away from the north and toward the south. Doesn't that mean that the compass needle points toward the south and away from the north? Remember when you were 5 years old? You sent Santa that letter and you never got the toy that you wanted when you were 5 years old? Here's why. Santa Claus doesn't live in the North Pole. Santa Claus lives in the South Pole. You sent the letter to the wrong place. That's why you didn't get what you wanted. The penguins down there in Antarctica were laughing their heads off because all these letters showed up to the penguins. They're laughing their heads off. He's not getting what he wants for Christmas again this year because Santa's not getting a letter. Listen, geographically, North Pole is Canada, but magnetically, North Pole is Antarctica. Now, when we navigate, we say that that is north. Okay, we say that northern Canada is north. That's okay. It's not right. Magnetically, it's not right. But as long as everybody's using the same language, it doesn't really matter, right? The problem only exists if some people are saying that's north and some people are saying that's south. When we're navigating, we follow the conventional rules. But technically, it's not north. technically, that's magnetic south, and that's magnetic north, at least for the next couple of hundred years or so, until we get a magnetic field, possibly a magnetic field reversal.